or the fluorescence, right? You have light source, right? You have light source. Okay, the light source actually, okay, the beam actually at, this is your sample. I just changed the cover of my screen, so it's a bit sticky. Okay, this is 180 degree. Okay, this is sample. Okay, your sample, your cuvette sample, and you have, of course, a detector. Oh, it's not very good, this one, because it's silicone, so it's sticking. It's sticking. This is your detector over here. Okay. Now, your UV visible spectrophotometer, right? Your UV visible spectrophotometer. You have the prism. You have the prism as well. Yeah, you have the prism. For the prism actually will refract the light into different colors, isn't it? If you remember, you have light coming in. Can't remember which one it is. So you have those different colors, okay, refractions, okay, and these colors actually detected by photo multiplier. The word is photo multiplier. It multiply the light signal, because the light we converted into electricity, okay, and then the electricity actually in currents, okay, current actually detected your units, your computer will actually read it as current. So this current actually what your computer actually convert it into the spectrum that you have. For fluorescence, right? Fluorescence, okay. Fluorescent cuvette. So either it is 180 degrees, right? Normally the cuvette is different, the fluorescent cuvette and the UV visible cuvette. You can use fluorescent cuvette for UV visible, okay, because fluorescent cuvette is four-side clear, okay. You are looking at 90-degree angles over here, maybe, or at 180-degree angles. So the fluorescent cuvette is a four-side clear because you are detecting the fluorescence at 90-degree angles, okay. The spectrophotometer, you are detecting at 180 degrees angle. Of course, you have prism, what is saying that diffracting all these light, right? You have detector there, okay. And you can use the fluorescent cuvette for UV visible because it's a four-side clear, but UV visible cuvette absorption, to measure the absorption, the cuvette is actually two-side clear, okay, at 180 degrees. And that's like slight difference between the two cuvette for measuring the fluorescence and absorption. Okay, phosphorescence is also the same. Okay, and now if you have fluorescence spectrophotometer, you can actually pump in certain energy of light to get the absorptions. Okay, to get absorptions, and typically, if you want to get fluorescence, right? You want to get fluorescence. Let's say you have this on your left-hand side, you have a benzene, isn't it? So you can actually pump in energy. So this is maybe 240, 220, maybe 230, okay, nanometer. Okay, 230 nanometer. So you pump in this energy because the energy, remember we're talking about excited energy level, okay? Is the ground state. This is 230 degree nanometer energy. Okay, you must actually pump in higher energy than your first excited electronic state. Okay, so and you measure the fluorescence. So you measure the fluorescent emitting light, right? Then energy that you pump in must be greater than the absorption energy, right? So that you can get all this. And let's say you have this kind of absorptions. Okay, this is just for descriptions. You have this kind of absorptions. Okay, remember these absorptions actually from multiple molecules, many molecules. Okay, molecules. Sorry, this is molecules. Okay, many molecules. Okay, this area under the graph is actually telling number of molecules. That's why the concentration, this one actually proportional to concentration. Okay, and area graph is actually the number of molecules, moles of the molecules. So this is proportional to the concentrations. But remember, this is population, which means there's a group of molecule absorbing at this wavelength. Okay, one molecule may be absorbed at this wavelength. One molecule. So remember, one molecule can take one photon, isn't it, to be excited? So only one molecule is over here. This is maybe third or fourth molecule. So there are many molecules underneath. So this is number. So population. Maybe this one is 100 molecule. This one maybe 70 molecule. This one maybe 100 molecule that absorb in this particular wavelength, that give that particular wavelength. So this is your spectrum look like, actually telling us number of molecule, number of mole. Okay, and the intensity reflects to or proportional to the concentrations. Okay, not exactly of the concentration, but you have some ideas of the concentration of your solutions, right, with the intensity of absorption. Similarly with the fluorescent and phosphorescence. Okay, they were similar case. Okay, let me see. Okay. Right. Okay, that's our last lecture note. So we just continue. We hope that we can finish this within our lectures. Anybody coming? Let me know. So okay, the next slide is on graduation to the ground state. Remember, so the relaxation actually within the vibrational states of the molecule. So you have this from the ground state, it goes to the first excited state, electronic state, and this is actually relaxations. Okay, right? It relaxed down to the ground state. This one also is relaxed down to the much lower state. So this is intersystem coasting. Okay, this one intersystem coasting. This one will give you fluorescent. This one give you phosphorescent. Right? This one give you phosphorescent. Okay. And of course, I'm just focusing at the bottom here. Okay. So it's a non-reactive singlet energy transfer in which the initial excited molecule did not. This is once the molecule actually absorb the energy actually can be transferred. Okay, either transferred to the triple state or can also be transferred to the neighboring molecule. Remember, we have many molecules in the solutions. Okay, not all the molecule actually absorb the light. Some actually not even exposed to the light of radiation. So, or the energy of light is insufficient, for instance. Right? There's many reasons why the molecule actually not absorbing a light. So now, if you look at the energy level between talking about vibrational state just now, okay, My room is very warm. Okay. So when we draw lines, it's just like when you draw the 1s orbital, 2p orbital, and all those. So we are drawing just a line indicating probability of finding the electron. Okay. When you draw the Jablonski diagrams that we had in the previous lecture, right? The Jablonski diagram, we just draw a line basically, right? We just draw lines, but bear in mind when you talk about the line that we draw, we're drawing the electronic energy level of the molecule. Okay, electronic energy level of molecules, and we have the vibrational state. Okay, we have the vibrational state. Within the vibrational state, we have the rotational state. Within the rotational state, we have the translational state. So the word actually describes, the molecule itself. So you have molecule which is twist, round, turn, vibrate. Remember, if you run FTIR, you're talking about, the two neighboring, because you have molecule, the two atoms actually, whether it's like spring-like and so on, pen, scissors, and so on, and so on. So you are actually measuring that energy level, right? FTIR infrared. So it's very small in the energy level. Infrared, remember, we're talking about UVC, UVB, UVA, and then you have the visible, and then you have the infrared, infrared, you have far infrared. So infrared is much smaller energy. So that's what you are measuring in the FTIR. Okay, so every time you draw the electronic energy level, so you have to bear in mind what you have in each energy level actually. And if you look at the translational energy level, which is within the rotational within the level, basically if you draw lines, right? If you draw the energy level, so you have many energy level type of energy level, and basically then you have the rotational, and within rotational you have translational, of course, and eventually it's just like the whole thing is actually possessing certain energy level. Okay, so if you look at the photochemical reactions, okay, the first one is primary photochemical reactions. Okay, the primary photochemical reaction, this one actually products are formed. Okay, product are formed. Okay, the secondary photochemical processes, immediates are formed, right? Immediate are formed. Okay, and the third photophysical processes actually compete with the formation photochemical, and this one actually involving deactivations of the excited state. Okay. Okay. So quite unfortunate that you actually are not experiencing carrying out some laboratory experiments in your first year, second year, or in third year, but enough. I think at the moment you just if you can imagine some of reaction, you have reactants exposed to maybe hydrogen lamps, okay, that carry certain enough energy to create for your reactant to absorb the light and then become a certain state or turn into radicals, and you have radical reactions. So this is one of common reactions. You have radicals formations, and just like we are discussing on the ozone formation, right? You have the oxygen radicals and further reaction of the oxygen radical. Eventually, will eventually form O3. Okay, from O3. Right. So this one is just simplified. This one I actually grabbed it from Atkin. Right. So we look at the some of the photochemical processes. Okay. The first one is ionizations. Remember, this one involves radical, which is not here, right? Ionizations. So you have excited molecule, which is, remember, before it become excited molecule, you have basically A, you have light, and you have excited A. Okay. So that's ionizations. Okay. And on the right side, actually the examples on the right side, okay. Secondly, on the electron transfer, okay, electron transfer reactions, okay. So you have similar A excited A react with B, and then you become A and B, okay, or A minus B minus, B plus, okay. And then you have the dissociations, right? Dissociations. If you have azo compounds, right? This is molecule R1, R2, right? So you can actually split the molecule. So you have nitrogen, and you can split the molecule. This is azo compound, is very typical. So this one we have example, for instance, splitting of ozone, right, at 1180 nanometer. Okay, you have oxygen and O2 oxygen molecule and oxygen radical. Okay. Secondly, dissociations, right? Thirdly, so we have ionization, we have electron transfer, we have dissociations, we have addition. So electron transfer, later on, we are talking about photosynthesis. We're talking about photosynthesis. Okay, that's involved electron transfer reaction. And then we have additions, right? So then we have abstractions. Okay, we have abstractions, and we have isomerizations, isomers, right? So rearrangement and the rearrangement reaction. So either you have either isomerizations, rearrangement also involves some critical reactions, photochemical processes. So we have, this is some of the examples that for this topic. Okay. The next topic, so I just move on from topic. Of course, when we are talking about light being absorbed, right? We have to find out how much actually the light being absorbed. Okay. So the quantum yield we define as number of photophysical or photochemical, right? That lead to primary product divided by number of photon absorbed. So how much actually this one yield a product, right? The photon, how much a product absorbed, 100%. Photon being absorbed, 100 molecule absorb 100 photon, and then convert into respective 100 product, for instance. All right. So if you have less, that is, we define the quantum yield of that particular event. Again. Okay. So the rate, right? You can actually define it as rate of the process divided by the intensity of the light being absorbed. And you can do that because rate is how fast the product being produced. Okay, remember, if you have 1 million of molecule, right? You pump in, let's say 1 million as well of the photon, right? Out of 1 million, and would the 1 million actually absorb the light? Or maybe that one we have 100%, right? We have one. If you have 800 photon absorbed, so by 800 molecule, okay, and then you produce how much of the product. That is, we're talking about quantum yield, because the word is yield here, right? The word is yield here. Okay. If you have, now we don't see it, but we can see the rate of reactions, right? We are talking about 800 molecules that absorb and turn into a product. So out of 800 molecules, it's not all the molecule actually, simultaneously producing a product. Okay, not 800 molecules simultaneously react and produce a product. That's a second sentence I put in. Not 800 molecules actually necessarily producing a product. Okay, so let's say we assume the 800 molecule from 800,000 from 1 million rule, the 800,000 from 1 million molecule actually going to produce a product. So it's not as simultaneous kind of all together at one instant. No, actually one by one, or some, or quite a number produced at this particular times, and then some numbers of molecule produced at this particular time. So eventually we got the rate of the process. So how fast? So basically the quantum yield, actually the sum of primary quantum yield or photophysical probability, eventually all actually equal to 1, right? Total. So this is sum of primary. So each one of it. Okay. So you can have number of event divided by the photon of number of photon being absorbed. So how much being produced and how much number of photon being absorbed. So this is, the word is yield, how much is being produced for that particular process or event, right? So we have just now, you can actually determine directly from rate, right? So typically this is what we can do in the laboratory, right? You can determine directly from the experimental rate, because this is determined, right? Can be determined. Okay. Okay, this one can be determined. Okay. Right. So let's say the event, the yield is emission. So let's say the yield is emission. Okay. So how much actually being absorbed, and that how much actually yield being emission. So remember I mentioned just now, so area under the graph, right? This is actually number of mole, right? This is number of mole. And how many? Telling us, okay, how many molecules, okay, right? Area under the graph, okay. So it tells us, okay. So if you have very thin absorptions, right, compared to very broad absorptions, right? So I mean, we can see immediately this one is, right, more. You have more molecule, exactly. Okay, right. So I'm moving on. Sorry, I have to speed up because I have another appointment, and then I have to see specialist almost. That's why he asked me to come today. So it's almost immediately. Anyway, so I try to finish as soon as possible if I have to cover this topic today. So the photophysical, the word is photophysical, right? Remember photophysical, photochemical in biochemical reaction. Photophysical is physical, light, heat, those are physicals, right? So this is I just mentioned earlier on about A. So basically you have, in this case, if you look at this, right, it said denote a singlet state, right? Not a singlet state. This one sometime third body. Okay. Now S here sometime denote sensitizer molecule. Okay. Sensitizer molecule S. So the word S. So sometimes they use as a singlet state, sometimes they use as sensitizer, or basically, the primary molecules. Okay, M, normally third body or third body molecule. Okay, the third M. So this is very typical. Normally books, all books, reactions, theoretical reactions, they use S, M. This is very common. And A and B is for explanation. So S, normally they indicate some sensitizer molecule. So the first one is absorptions. Absorption, you have molecule, right? Absorb light energy, and then it jump to the electronic state, right? Excited state of the molecule. Secondly is the absorptions, excited state absorptions, right? This is when you pump in energy in picoseconds, laser, right? And so on, pico 10 to 15, right? This is very fast. So the excited state of molecule doesn't have time to relax down and come down to the ground state. Okay, fluorescence, right? Fluorescence, you have excited and then come to the ground state, producing the fluorescence, right? Simultaneous emissions. Okay. Also, yes, intersystem crossing, we mentioned. Phosphorescence, also internal conversions, relaxations. Okay. Coming down, collisions induced. Okay, collision induced. So this one either emits, sometimes it's actually electronic or energy transfer reactions, electron transfer or energy transfer reactions can occur both singlets and triplets. Okay, excimer, sometimes we call it excimer molecules, so S, right? And the energy pooling, this is quenching of, because you have to have same molecules, the donor molecule, when you get excited, the excited state of the donor molecule must be higher than the acceptor molecule. So this particular one, if you mention 1 and 2, okay, let's say this one goes to 1, this one goes to 2, okay. So remember, we have S1. So over here, S1 is, it goes excited here, and then eventually it's relaxed. But S2 may be absorbed at much higher wavelength, a much lower wavelength, and then as it come down, maybe once in the this vibrant state, it actually undergo or quenched by S1 here. This one S2, right? Okay, right. So now, once the molecule actually absorb, right, absorb the energy, it goes to the electronic excited state. Okay, it can actually come down. Eventually, come down to the ground state, right? Eventually, come down to the ground state. So the decay, if you have some watch, some watch that at night it actually the numbers in your watch has this white strip, and this white strip actually give you some phosphorescent emission. So it's bright, and if you turn the light off, okay, and you notice it eventually the intensity of this light actually diminishes, right? So it becomes dimmer, right, over a period of time. So it doesn't last the whole night, for instance. Okay, some good watch is actually lasted quite long. Or you have, if you go fishing, yes, you go fishing, right? There's a fluorescent rod that you normally put it in on the tips of your fishing rod, right? Or you have buoyants, for instance, you put on the buoyant so you can see from a distance, because it emits light. Okay, and after some times, you actually it losing its intensity. Okay, losing intensity. So you losing the light, which means the molecule that produces the light emits light, eventually the molecule actually losing the excitations, right? Excitation. So you can, this actually is measured by the decay. The excitation intensity reduces over time in exponential manner, right? You can curve fit that in, and then you can get the rate of decay, whether for fluorescence and whatever molecule you have, right? Or it doesn't emit light. It come down. You still can actually measure that using laser setup, right? As the molecule actually coming down to the ground state, without looking at the intensity of the emissions. Okay, so fluorescence, for instance, right? It emits coming down, so emits light, so you can determine the rate of decay for fluorescent. Of course, it depends on the concentrations of the number of excited molecule. Okay. Similarly, with intersystem crossing, internal combustion, similarly with intersystem crossing. Right. So overall decay, right? Overall decay, right? So you have the overall fluorescence, right? Because this involves those events simultaneously in the system. So overall rate of decay, right, is a sum of all these processes, right? Of course, the rate are different, isn't it? Last time you look at the rate, they are different, 10⁻⁶, 10⁻11, 10⁻12, so on. So the rate are different. So the smallest one normally does not contribute as much. And you measure using your instruments, right? Because it's very much faster. You just observe which is the one is very slow, because that one is relatively step. So those are actually very little to measure, right? So when it turn off, so you can actually measure. Okay, remember this is actually an exponential, right? So you can, the tau actually 1 over all this rate constant, and you eventually get, this is time, this is intensity, right? You have rate of decay. This one at particular time at lambda, huh? At certain lambda. You measure it to lambda. So you have the rate of decay overall. Okay, right. I want to check if anybody actually coming in. Just bear with me. No, no one. Right. Okay, you got my slide, right? So similarly, right? If you look at the steady state approximation, steady state approximations, this one overall give you 0, right? Overall. So um, but it is actually the sum rate constant multiplied by um, initial concentrations, excited concentrations, internal conversions, and the intersystem crossing. Right? The quantum yield of fluorescence, right? Remember, is a rate, isn't it? This one we discussed earlier on is the rate of absorption, So what you get is the overall the fluorescence over the rate of fluorescence plus the um, because this is total rate of the reactions, because this is reactions, right? This total rate of reactions. right? So what I'm saying here, this equation you can determine this one, right? Because what we get is overall rate of reaction, right? The whole rate of reaction. Now I talk about molecule that quenched just now. So the present of quencher, this one we denote as Q. S, remember, is talking about single S. So the reactions, right? The rate of reactions by molecule Q, right? Depends on this one is a constant. So we actually know that if Q, this one is S, this one is Q, so Q must have lower energy level. Okay, this one S, right? This one S star, this one is Q star. Yeah, when it comes down, it's fluorescent, isn't it? When it comes down, it's fluorescent. This is lowest excited electronic energy level. Lowest excited electronic energy level. Okay, lowest excited electronic energy level. Okay, because Q must be lower. So if you look at this, Q must be lower because the lowest S come down is over here, is still above Q. Right? The lowest S come down, the lowest energy state, okay, still higher than Q. So it can undergo, can quench by Q, right? And take the energy from the S, and now Q gets excited. Okay, now Q gets excited. This is just so you have S star plus Q, give you Q star plus S, right? Get excited. Okay, so similarly, like what we discussed earlier on, we back to the steady state approximations, the quenching, right? Now, the rate of reaction of the quenching process, okay? And if you have the rate, right, of the QQRT, and you can actually determine, this one actually you can determine, okay? And you have the rate constant, you plot with this, right? So you get that, sorry, Q, if you, sorry, plot this, the concentration, we got the slope over here, right? And you can determine Q as well, right? Okay, you can determine Q, you can determine the lifetime as well. So this is called thermal. Okay, and okay, I just basically you I naught over IF, right? You plot in Q. Actually, this one you can get KQ and KF, right? The rate of quenching and rate of fluorescence, and you can determine this, right? Determine that as well. Okay. On the slope. Okay, this is one example. This is one example you are given. Let me just see some of questions. Okay. So what you get is from this equation, actually you get a line, right? So the slope, okay, the intercept, right? Once you get the intercept, you can get the overall rate constant, right, from this particular reaction. Okay. So okay, so reaction we have here. This one and just now, Electron transfer, you have one dot there, one dot, so because it just take one spin of the electron, right? You just take one spin of the electron because you have to turn it out and down, so you just take one spin of it. So normally in a pair in the orbit, take one of it, so you are transfer one electron at a time. Okay, right? And just quickly, right, remember this way we approximate in the steady state approximations, right? So overall is equal to 0. Okay, all these reactions is not one single reactions, right? Some involve many steps. Okay, but overall of process and also process quenching reactions, basically remember actually the sum of all of this. So this is absorptions, right? So this is the emissions, losing it. This is the internal conversion using the state at that particular time. Intercourse to some point you actually the energy transfer to different states of electronic state, excited electronic state, and then the quenching basically you also transfer the light energy into the neighboring molecule. It could be similar. Okay, this one quencher could be S as well. So you have S excited and plus S. Okay, I just label 1, 2. Just label, just a label. So you have S plus S1 plus S2. Okay, S1 plus S2. Now the reason why this is possible, right? Because S and S, S1, S2, right? They have similarity. So the energy transfer, electron transfer, the lowest excited energy level, excited state energy level, right, must be equal. Must be equal. This one must be equal. Then it's possible for the energy or the electron to be transferred to the neighboring molecule. So same molecule can quench as well, right? Same molecule can quench as well. Okay. So if you plot, now you can actually look at this. You plot this one versus this quencher concentrations, right? So this one basically y equal to mx plus c, right? C. Okay, so kf actually the intercept, right? Okay, intercept at y-axis. Right. Once you determine the kf, you have kq for this particular one, then you can determine all the parameters. Right? Right. So I give example as well over here. You can try this example right in your lecture notes. Right, you can try the example in lecture note. Normally this one in your exam as well. So one of all these plots and this particular topic has many plots involved, right? Many plots involved because it's involved rate, quenching process, fluorescent decay, and things like that. So involve all this. So you can try it out at home, right? You can use this example and make sure that you can get all this value over here. This is example. All right. Okay. So this is a quantum yield. You can try that. Okay. I think that's all. Okay, guys. You still there? You don't go.
Yes.
Okay. Let me. Okay. Let me. You got class, right? I've taken your attendance just now. So I just a minute. Just a minute. I'm taking